Hello, everybody. Thank you so much for clicking on our video today. Our group is really excited to share with all of you that have clicked on the video an experiment to verify Newton's second law. But however, before we continue and we show you the derivations of the experiment, allow us to introduce ourselves. My name is Arish.
My name is Shajit.
My name is Al. My name is Abdul Rahim.
We all are part of a physics class at Curtin University, Malaysia.
So everybody, the objective of the project is to verify the Newton's second law. This one. And Newton's second law states that the net force acting on a body is proportional to the acceleration and mass. This one is net force proportional to mass times acceleration. However, before we explain our experiment, we have to divulge deeper into Newton's second law. Just now when we mentioned force, acceleration and mass, and this one is force, this one is mass, and this one is acceleration. What did we actually mean? What specifically do those words mean?
Force is difficult to define. Even in the scientific community, it's ambiguous. So for our particular experiment, we're going to say force is the push and pull of the object, while acceleration is the capacity to gain velocity. As for the mass of the body, it can be regarded as a quantitative measure of the resistance of a body to acceleration by a given force.
The experiment that will be used to derive Newton's second law consists of a modified version of Atwood's machine. For those of you that are not aware of Atwood's machine consists of two objects of mass connected by an inextensible string over an ideal pulley. Please refer to the animation playing. However, our version of the experiment involves replacing one of the blocks with a cart, and in this experiment, the acceleration of a cart will be determined by experimentally collecting data on velocity and time.
So in our experiment, the force T will be applied to a cart by means of hanging mass. The force T is in this direction. And if one can minimize friction so that friction can be considered negligible, then the net force in the direction of motion simplifies to F equal mCA, where mc is the mass of cart and the acceleration is towards the right.
To create as much of a frictionless environment as possible, we'll hang the weight that will counterbalances the weight of the cart. To verify whether our experiment is in equilibrium or not, we will push the cart with a slight push, so it will, and if it retains constant velocity, we'll say it is in equilibrium. So now I'm going to add 20 grams to the weight, and my friend there will give it a slight push. As you can see, the cart does not retain velocity, so I'm going to put 20 grams 20 grams more. Shit. As you can see, the weight, the cart still does not retain constant velocity, so I'm going to add 20 grams more. As you can see, finally the cart moves at a constant velocity at 70 grams of Henry mass. This happened because when the net force is zero, even when the net force is zero, even a slight acceleration due to push will produce velocity. This is because the frictional force has been set to zero, and it is cancelled out by the weight of the mass. Therefore, the same velocity should remain, and no friction will be able to take energy out of the system as heat.
Once the cart is in equilibrium, any additional mass added to the hanging mass will produce an acceleration downward. For our system, the hanging mass that gives us the equilibrium is 70 grams. So any mass added more than 70 grams will produce a downward acceleration for the hanging mass, which in turn will take the cart with it. So because we only have increments of 20 grams, our added mass will be 20 grams, and we will keep this throughout the experiment, no matter how many trials we conduct. The net force downward due to the additional mass will become F equals mf and g, where g is the gravitational acceleration and mf is the mass, is the additional mass, importantly. So for us, mf will all be 20 kg. However, the force of the additional mass is pulling on both the masses of the car and also the hanging mass from before. Therefore, this will produce an acceleration that would equal what you would get when applying this force to something that weighs the same as the sum of the two masses. This results in the acceleration being equal to force over the mass of the car plus the mass of, or the hanging mass, so to speak. Now, to derive our equation, what we can do is we can replace this f right here with this f. And when we do that, what we get for acceleration is mass, which is the additional mass, times gravity over the mass of the car plus the hanging mass.
The point of the experiment is to isolate g, which is the gravitational acceleration. So let's do that now. This is the equation. A mass of cart plus mass of hanging mass divided by additional mass equals to g. If the determined value is close to 9.8 meter per second scale, then the experiment will be considered a success.
In this equation, to find g, we need to find the mass of cart, the hanging mass and the additional mass, which are easily done by using a weight scale. For hanging mass and additional mass is stated on them. To find the mass of cart, we need to measure it using a weight scale, which we can do just right now. So this is a cart and we can measure it using a scale.
The acceleration can be found by using Newton's kinematic law, which is the final distance, initial distance plus initial velocity into time plus acceleration into t squared by 2. So to isolate the A, we move these to the left side. When we move the initial distance to the left side, we get final minus its initial, which makes up the height of the weight, which is this. So it becomes the height. As for the initial velocity, when the system is in equilibrium, it's at 0, the initial velocity becomes 0, so this is cancelled out. So we get height is equal to a t squared by 2. So we want the a, so we move them to the other side. So a is equal to 2h by t squared. Now we can get the acceleration. So after we get the acceleration, we substitute this in this equation to find the g. And if the answer for g is close to 9.8, we'll consider the experiment a success.
Okay, so guys, now to the actual experiment. For the actual experiment, as we found out earlier, the car is counterbalanced by 70 grams of weight. As you can see, including the hanger weight, this all equals 70 grams. According to our derivations, however, we need to find two variables. One of them is time, which I will do using my stopwatch with my phone here. The other is height. My colleague will find the height and let you know.
75.3.
Yes, so the colleague tells me that the height is 75.3, that is in centimeters. To do our derivate, like to actually find our values, we will convert that into meters. Now, once my colleague is ready, he will count down and I will start the time watch and let's do the experiment.
1, 2, 3.
So there you go. I stopped the time watch right as it hit the floor. The sound was a great indication. As you can see, the value I got was 2.29. Now let's take that to the board and let's find the actual value of G using the values that we found experimentally. So as you guys saw in the experiment, we got the data for our trial number 1. Unfortunately, because of time constraint for this video, we conducted trial number 2 and trial number 3 behind closed doors. We don't want to make the video longer than it has to be. And the important thing to note about trial number 2 and 3 were we conducted them at the same height. So we literally would move the hanger mass up to that height and then we conducted the experiment. And the time values that we got were these. To find the acceleration value that will help you determine the gravitational value, we use the formulas that we had derived earlier. As you see, the acceleration equals to 2 times the height over time squared. Why don't I show you how to get this value by actually doing it? So the acceleration would equal 2 times the height. Height for us was 0.753. Note that this is in meters. What my colleague told you was 75 centimeters. And all of this divided by time squared. Our time is 2.29, as you saw on the stopwatch. This gives you a value of 0.29. It's important to note that this 0.29 is to 2 significant figures. To find the gravitational value, we go back to our formula right here. Now that we have A and we already know the mass of the card and the hanging mass and the additional mass, let's try to get that value. The mass of the card is 611.27 plus the hanging mass was 70 grams. This is divided by the additional mass. For all of them, we kept the same additional mass as we had stated earlier, which was 20 grams. Please note that these values are in grams and not kilograms. The reason for this is the grams will cancel out. So even if you do convert them to kilograms and kilograms, they will still cancel out eventually. So you don't need to actually convert them because of the ratio.
Yeah.
And for the acceleration, if you look at the acceleration, we just use this value. 0.9. And the gravitational value that we get is 9.78. 9.78. Now, like I said, all the other trials were conducted before, and so why don't we find the average? To find the average, we just add them and divide by 3. So if you look at our values, we get 9.78 plus 9.67 plus 9. I'm going to write it down because I don't have space. 9.87, and all of this is divided by 3, and the average value that we get after you put this in the calculator is 9.78. So as you can see, and if you do want to find the percentage error, it's really easy. You can find the percentage error by taking the theoretical value, 9.8 minus 9.78, all of it divided by 9.8 multiplied by 100. This value is less than 1%. Less than 1%. So this data that we have collected in our experiment actually works as a really good tool to prove to you that the acceleration is inversely proportional to mass for a given amount of force. The given amount of force for our experiment was given by the increment of 20 grams. And so overall, we're very happy with this experiment. Hope you learned something today. And I would like to give thanks to my group mates, Sharjia.
Thank you so much, guys, for your time.
as you can see, the theoretical answer we got was within the margin of error, so we can consider this experiment a success.
And if you have any questions, then please feel free to leave them in the comments. Thank you.
Thank you so much,
Thank you
guys.
so much.